Hello and welcome back to our lecture on descriptive statistics in our statistics lecture series. As promised, we are going to be continuing this lecture with a part about variability and shape. So let's just hop right into it. So variability is going to do a couple of things. It's going to describe our distribution because it's a descriptive statistic, and then it is also going to measure how well an individual score or group of scores represents an entire distribution. Basically, it's going to tell us the extent to which the scores are spread out, how much they spread out, and how much they vary from the mean. Again, a note actually is that measures of variability tend to be used in conjunction with the mean or with the measures of central tendency. We often describe variability in terms of how far away something is from the mean or from the median. Again, we're going to look at three measures here. The first we're going to look at is the range, which is just the distance covered by a distribution. Then we're going to talk about variance, which is the spread of scores within a distribution, which is a little different. And then standard deviation, which is the average distance that scores deviate from the mean of a distribution. And we're going to build up to each of those. So the first one we're going to talk about is the range, which is the simplest and most obvious way to describe a distribution about how spread out the scores are. It is just the distance covered by all the scores from the smallest to the largest. As you can see here, you calculate it by subtracting the lowest score from the highest score. And it's used when it's important to know the greatest possible distance among scores in a distribution. The problems with the range is that it is completely determined by the two most extreme values in a distribution, and it ignores all of the other scores, which means that it's not really a reliable method in terms of describing range or in terms of describing spread. It's great at describing range. That's what it does. So yes, the disadvantage here are that it's greatly affected by outliers and tends to be unreliable. The best and most commonly used measure of variability instead of range is actually standard deviation, which we're going to talk about a little later. Okay, but before we can talk about standard deviation, we need to talk about where it comes from, how we got to standard deviation. So first we have to talk about the mean deviation. Mean deviation is a little different than standard. It's just the average distance of each value from the mean. So you're going to calculate the deviation score, which is just the distance of any value from the mean. Excuse me. This can describe to us whether scores are clustered closely around the mean or whether they're widely scattered away from the mean, which can be really helpful. The problem with this is that according to one of the properties in the mean, if you remember our last lecture, the sum of deviations from the mean is always going to equal 0, which means that the numerator of your deviation score is always going to equal 0. You can see that here, right? These are all of the values in our data set. The deviation of each value from the mean, if you add it all together, the summation is just going to be 0, which is not actually very helpful. So what we do to fix that is we find the distances or the absolute value from the mean instead. So instead of saying that we're going to take -3, -2, 1, 1, you're going to take the absolute value, so just the distance. And that solves that problem. Our numerator is now no longer 0. So how we calculate this is we sum the absolute values for each score's deviation from the mean, and then we divide it by the total number of scores. Although this is a pretty good descriptive measure, it's fairly robust. It's rarely used because the mean deviation doesn't fit well into more advanced statistical procedures. But the good news is that there is a different measure that's closely related to mean deviation that does fit well with statistical procedures that are commonly used, and that is, spoiler alert, standard deviation. But in order to get there, there's one more intermediate step we need to talk about. Sorry, this is the overall score here. That's the mean deviation. Okay, so the next one we're going to talk about is variance. Here, the difference between variance and mean deviation here is that instead of just taking the absolute value and adding it all together, we're just going to square. We're going to add all of the distances from the mean, and then we're going to square them, then add them together. And this is called the sum of squares. The sum of squares is the sum of squared deviations of each value from the mean. So you take each distance, you take the distance of each value from the mean, you square each of those, and then you add them up. That's how you get the square of sums. And that is the numerator in our variance formula. This is an important statistic because, actually, maybe I'll talk about that later. Yeah, we'll talk about that a little bit later. But the note is that the squaring is going to eliminate the minus sign the same way that using the absolute value eliminated the minus sign in mean deviation. The reason that we use the sum of squares is because, actually, we'll talk about that in a second. Let's move on for now. So one of the disadvantages of variance is that it's not very useful as a descriptive statistic because it's based on squared units, which doesn't really provide us a good measure of the spread of a distribution. You can see here that the variance is 8.67, while the range is just 7. So the variance is actually sometimes larger than the extreme range of the distribution because it's based on squared deviations and not just the normal deviations. The obvious remedy to this problem is that we're just going to take the square root of that because that just cancels out. Well, it doesn't cancel out, but it helps remedy that problem. Taking the square root of the mean square provides us with a measure that produces a good description of variability of the distribution and actually also fits really well into more advanced statistical procedures. So it solves both of those problems for us. And that leads us to the standard deviation. So we're putting all of those formulas together. We're just going to find the variance and take the square root of it. And that is standard deviation. We also need to make it clear, I want to take a second to point out that squaring, averaging by the total, and then taking the square root is not the same as just averaging the absolute values. The square root and the square don't cancel each other out because of the order of operations. If the two procedures were equivalent, then the standard deviation would always equal the mean deviation, and that's not the case. The process of squaring and then averaging and then taking the square root just gives some extra weight to large scores, which is the whole point of a standard deviation. We give extra weight to large scores because we're looking at the variability. We're looking at how much the distribution varies. So that's why this process is important. Okay, I think that that's actually going to be good for this. I will also say that the sensitivity to large scores is generally good, but it can be a problem if there's a few very extreme scores in distribution, outliers, if you will, which can result in a misleadingly large standard deviation. So just the way that we look out for outliers when we're calculating mean, we need to do the same thing when we're calculating standard deviation. Okay. So thus far, our discussion of variability and standard deviation, has been limited to a situation in which we're describing the variability of an entire population of scores. However, often when we're using inferential statistics, like we've talked about before, we're actually we're running our experiment, our research on a sample, and then we are generalizing and drawing conclusions about the whole population. So we've been talking about population parameters. Now we're going to talk about how these measures of variability are a little bit different when we're measuring them for sample statistics. This table is really important here. It's just showing the differences in symbols between what we use for the population and then what we use for the sample for the same things, mean, variance, and standard deviation. Okay, so a problem arises when variance is calculated, or when the variance that we have thus calculated is used to estimate the variance of a larger population. The problem with that is that the variance of the sample tends to underestimate the variance of the population. This is called bias when a sample says that when a sample's variance is calculated as smaller than what the actual populations is, that's called bias. And I'll show you an example of that, right? Or you can look at this graph here. The sample variability that we took from our population is just from this X value to this X value, which is smaller than the overall population's variability. And that's a problem. The way that we get over that is instead of just dividing by n when we're dealing with sample statistics, we actually are going to divide it by n minus 1 instead. This is how we account for bias. One of the effects of that is if we have a bigger denominator, that means that our resulting value is going to be a little bit bigger. So that accounts for an underestimated value, right? If the value is smaller than it's supposed to be, we just create a bigger, we make a smaller denominator, which gives us a bigger overall value. Let's talk a little bit more why n minus 1 is an appropriate assumption to make when we're calculating unbiased statistics. The reason for this is involved with this topic called degrees of freedom. And I don't know if you can see that. Okay, there we go. Let's say that we have a data set that looks like this. We know that one value is 1, one value is 3, but we don't know what the last value is. However, we know that the mean is 4. Now let's calculate the distances of all of our values from the mean. The distance of this from the mean is -3. The distance from this from the mean is -1. And we don't know what this distance is from the mean. However, we know that all the summation of all of the distances from the mean equals 0. That is always the case. So if we know that this has to equal 0, and we know that we have a -3 and a -1, this value has to be -4. That is constrained. That's what it has to be in order for it to fulfill all of the laws of statistics. So thus, if we know what 2 of the deviations are, the third deviation is set in stone. So that means there's only room for these 2 deviations to vary before all of them are set in stone. In other words, all of the scores except for 1 are free to vary from the mean of the distribution before you have a data set that is set in stone. And because of that, we say that any given distribution generally has degrees of freedom of n minus 1. And so that's why we use that as the denominator here, in our unbiased sample statistics. Okay, let's move on from that. So let's talk about some of the properties of standard deviation. I also want to make sure that you can see everything here. Sorry, let's try to make that a little smaller. Okay, so some cool information is if a constant is added or subtracted to every score in a distribution, the standard deviation actually will not be affected. It's not going to change because the mean is going to move relative with the scores. The scores stay the same relative distance away from the mean, which is what the standard deviation is measuring. So if you add or subtract a constant from every score, standard deviation stays the same. However, if we multiply or divide every score by a constant, then the standard deviation is going to be multiplied or divided by that same constant because the spread of our distribution is going to change. Oh my goodness. Okay, now let's look at how we can represent variability graphically. So in this situation, the mean here and the standard deviation, we can use them to reconstruct the x-axis essentially. Because when we're graphing, when we have any type of graph of a data set, the mean is going to be, we're going to set the mean up in the middle. And then each section that we see under the graph is going to represent the distance of 1 standard deviation away. So if this is the mean plus 1 standard deviation, this is the mean plus 2 standard deviations, and this is the mean plus 3 standard deviations. So because of that, we can reconstruct the x-axis. 1 standard deviation, 2 standard deviations, 2 standard deviations, 3 standard deviations. And this is how we reconstruct that. Each of these ticks represents these. So if we were to use, do the same thing, but using actual numbers, let's just practice this a little bit. If we calculated our mean to be 50 and our standard deviation to be 10, you could fill in every single one of these numbers just from that information. You just plug them right into your formula. If this is the mean plus 1 standard deviation, it's going to be 50 plus 1 times 10, which is just going to be 60, then 70, then 80. And then this is the same thing, but just subtracting it. 50 to 40 to 30 to 20. This graph shows us how, if we change our standard deviation, the graph, the representation under the graph stays the same. Each of these ticks still just represents one standard deviation away from the mean. But if the standard deviation gets smaller, then our spread gets smaller. Our spread gets narrower. This is a standard deviation of 10. This is a standard deviation of 5. And we can do the same thing reconstructing the x-axis. Instead of this being 60, now this is just going to be plus 1 standard deviation, which is 5, 50, 55, 60, 65, and same thing, but the other direction, negative. Okay, now before we move on, let's just look at some helpful information for reporting your results in the most effective way, reporting your descriptive statistics. So in general, if you need to represent less than or equal to 3 numbers or 3 statistical values, just use a sentence, put it right in your text. If you need to use you need to present, between 4 and 20 numbers, use a table. More than 21, use a graph. And another note is, if you present your statistics in a table or a graph or any kind of figure, you don't need to repeat them in the text, but you should mention the table or the figure where that information can be found, and you should emphasize whatever data helps your narrative. Mention the specific statistics that help construct the story of the manuscript that you're writing. That's okay. You just don't need to write all of them down. Here are just some statistical symbols that we're going to be talking about here. For population parameters, you're going to use non-italicized Greek symbols. So whenever you see a Greek symbol, it's representing population. Whenever you see a Latin letter and it's italicized, that's going to be a sample statistic. A capital N is the number of members in a total sample or population. A lowercase n is the number of members in a limited portion of your sample. And last thing is, when you're writing out mathematical text, do you space it the same way that you would space words. Put spaces in between every letter and function, because otherwise this is way more difficult to read. Yeah, it's like words without spacing. So just put spaces in between. Here's an example of a good standard way to report descriptive statistics of a sample. You can take a screenshot of this, come back and reference this. We'll talk about these, how to report results by APA guidelines more in the next couple lectures, but here's just a reference for you. And one more reference of how you would report your statistics in a table, and then how you would talk about them in the text. Okay, and with that, we're going to end this discussion of descriptive statistics, and I will see you in our next lecture.